Hi, everybody. You should have your worksheet with you. It's two pieces of paper. The first one's front and back, and the back one is just the front side of it. There's a little picture there at the bottom that has an A and a Z and an X. So if you do not have your paper, you can go to Fusion and access it and print yourself a new one so that you can turn in your assignment. Alright, so we've been talking a lot about states of matter lately. So you see there at the top of the page, an example of what you were supposed to draw on your recent worksheet. And the great thing is that almost everybody got this part right. So that's excellent. I was excited to see that. So there on your worksheet, if you would fill in the missing words for the definitions for solids and liquids and gases, you can see that solids are closely packed together. They're very orderly arranged. They are moving. They vibrate against each other a little bit, but it's not moving a lot. Liquids are still touching one another, but they're not really arranged in any specific pattern for the most part. They move around a little bit more because they have more energy, and that movement allows them to change shape, to slide around. And then gases have the most amount of energy. There's pretty big distances between them. They don't usually touch each other at all. And they move around very quickly and very randomly. They don't follow any specific sort of pattern when they move. So here we have this red maze. Go ahead and solve the maze. What's the problem? Why can't you solve the maze? Would it help if the maze looked like that? How is that different? And in what ways is that like the question that you were asked recently about why you can't swim through solid ice? So the answer is not just the ice is solid. Well, yeah, it's solid, but why can't you swim through a solid when you can swim through a liquid and you can walk through a gas very easily? So then we have this one. How is that even better, and how is that different from the first two? Go ahead and make sure you answer those two questions on your page. Pause the video if you need to. So you can see there are pictures again of solid, liquids, and gas particles, and the empty space between them is what allows the shape to be able to change. Fixed shape means it doesn't change, and variable means that it does. So something with a fixed shape is a solid, like this dice. If you put it on your desk or in your pocket or in a box, it's still the shape of the dice. A little piece of sugar cube, a soccer ball, all solids. Don't change their shape. Their shapes are fixed. Variable shapes are liquids and gases. So maybe something like this water bottle. Try not to think about the bottle. The bottle, of course, is a solid. Imagine just the water that's inside it. And all that water is shaped exactly like the inside of the bottle. It fills the whole part up till where the volume of the water stops. It does not fill the entire container, of course, unless you fill it with more water. How about water drops that are splashing like that out of a puddle? They have a different shape than the water that's in the bottle. So unlike with the solids up here, you don't. Do you see how the shape is different? It's not always the same shape. The water that comes out of the bottle here is not still shaped like the inside of the bottle. How about this glass? That one's shaped like the inside of the glass. How about the puddle under these person's boots? It's all spread out. That puddle doesn't even have any kind of container. So it spreads out as much as its volume will allow it to. And then water that's dripping out of a faucet takes its own shape. All these shapes are different. And then we have a different glass that's shaped in a different way. And so all of that water is shaped differently. So all liquids will always be shaped like the inside of their container. And if they have no container, they will spread out as flat as they possibly can. How about a gas? Don't think about the balloon itself. Think about just the gas that's in the balloon. It's shaped like the inside of the balloon. It's kind of a funny oval shape, or maybe an upside down teardrop if you want to think of it that way. How about if we had heart-shaped balloons? Then the gas on the inside is shaped like a heart. What if we had a Mickey Mouse balloon? The gas on the inside is shaped like Mickey Mouse. Sorry, I didn't have a picture of a Mickey Mouse balloon, but you get the picture. If you pop that balloon, that gas does not stay that shape at all. It doesn't even stay that volume. It will start to spread out forever until it reaches the sides of some other container. So if it's in a enclosed room or maybe inside of a vehicle or something, all that gas will spread out till it can't go anymore. If it's outside, it will technically spread through the whole atmosphere sooner or later. So variable shape is for liquids and gases. They will be whatever shape they're contained in. So let's look at this. One of my favorite movies is The Wizard of Oz. And since it's almost Halloween, I decided to use little witches here. You see how the witches are arranged in a little orderly pattern? They represent the particles that are in a solid. You can see there's not really a lot of space to get through them. What if I had them kind of still close to each other, but not really organized in any specific pattern? That's more like a liquid. They're starting to move around, to be a little fluid. They're not in line anymore. They're not in that perfect grid structure. And then something like a gas, they're all over the place. They're really random. They're distributed with no specific pattern. There's not a lot of space. There's not a lot of touching, I should say. There's not a lot of order there. There's a word that you might learn later called entropy. And entropy is the measure of disorder. So many teenagers' rooms have a high degree of entropy. There's a lot of disorder there. Gases have very high entropy. They're very disordered. They're very random. There's no specific pattern to the particles in a gas. And for that matter, they're moving so fast anyway that even if they were ordered, it would only be briefly. And that doesn't happen. So let's think back to some of the questions that you were asked recently. Things like, can you walk through solid ice if you were swimming in a pool and it suddenly froze into a block of solid ice? A lot of people had some good thoughts and they were saying, well, no, of course not. I can't swim through ice because it's too cold and my body's not made to deal with that kind of cold, like a polar bear or something. And that's absolutely true, but that's not really what we were getting at. It's getting at, why is it that you can't move through a solid? Why is it that you can sit on a chair and not fall through? Why is it that you can walk on the solid floor? Solids have no space between them for the shape of it to be able to accommodate any kind of variation there. Do you understand what that means? It means that all those particles inside the solid are so locked into place that you couldn't move through it. That is what a solid is. So now if you think back to swimming in the swimming pool, the reason you can move through the liquid is because those particles can move more easily. There's space between them. You can actually take your hands and part them and change the shape of the water around you. Now think about the question you were asked where they said, could you build a building out of liquid? And you can't. It's not possible. Liquid does not build upon itself. It has no structure. It doesn't keep its shape because all of these little particles that are inside of it will just slide right on past each other until they run into a solid, actually. Now what happens here is that as it went from a solid to a liquid, it got warmer. I know that's a hard thing for a lot of people to grasp. Solids are the coldest version of any specific type of matter. Think about an ice cube. An ice cube is colder than just a bottle of liquid water. So when it goes from a solid to a liquid, it has taken more energy. It's moving around more. That's what allows its structure to be a little bit more random. And then once we get to a gas, if that's getting even warmer, it has received even more energy. So you are walking through gas all the time. Look around whatever room you are in. That's not empty space in front of your face there. That is a whole bunch of gas. And you are walking through it and sleeping in it all the time. You can move through those particles no problem at all. Because there's so much space between them and because they're moving around so much, because they have so much energy. Now, technically, gases can keep getting warmer forever because there's no limit to how much energy you could get. Now, if you weren't on Earth, a lot of types of gases could become plasmas, and there are a few things that become plasmas on Earth, but we won't really talk about those because they're very rare. Plasmas are not that common, and there are not a lot of opportunities for you to observe them directly. So try not to get too caught up with figuring out what a plasma is. So if you look at this little graphic here, we have solids all the way down there on the bottom left. And then it says that we add energy and go up to liquids. And then from there we could add energy and go to gases. And from there you could add even more energy and end up with plasma. And you see there's a picture of the sun over there. It says stars because remember the sun is a star, just like all the other stars that you see in the sky. The sun actually is a pretty average star even. It's not that big and not that bright. The only thing that's really special about it is that it's our star and we're really close to it. So you can see as the structure goes from a solid to a liquid to a gas, that degree of randomness and motion is a function of how much energy is being put into it. So if you would make sure that you fill in the parts of this here, under the right conditions, anything can be any state of matter. And I know that's kind of strange to grasp. You could freeze air. Air is a gas right now. But if you took enough energy away from it, it would change phase all the way down to solid. You could melt a car. Cars right now are solid. But if you gave them enough energy into those metals and plastics that are there, they could become liquid. You could even boil plastic. If you gave it enough energy to melt it, and then to evaporate it from there, because boiling is going from a liquid to a gas. Under the right conditions, anything can be any state of matter. It's just that many of those things are very unlikely to be able to happen on Earth. Certainly not naturally. Possibly if you were in some type of controlled environment, like a chemistry lab, maybe, you could force some of these things to happen. These are all called phase changes, which are types of physical changes. They don't actually change the chemical makeup of the substance in any way. Water, whether it's solid ice, liquid water, or steam, is still the chemical H2O. That does not change. So a phase change only changes the physical phase itself. And even though some of them are drastic, they're all possible under the right conditions. So I have another graph here. It kind of looks like the same one we just had. This is called a heating or cooling curve. And we'll get into some of these later in the year. And we'll start to do some calculations with them. You can see down here at the bottom they have kind of a close-up picture of the particles that are in a solid again. You can see that they're arranged pretty orderly, and they don't really show any movement there. You can see that it starts out at negative 40 degrees Celsius there on the y-axis. And as time goes on, it says that energy is being added if you move from left to right across the graph. And it goes up to 0, and then you see it stays 0 for a little while. While it's staying 0, all that ice is melting into liquid water. All that energy is going towards making the change of phase from solid to liquid. And then the liquid starts to warm up, and you can see the little picture here shows that they're a little bit more randomly distributed inside of there, and it's also showing that they're moving around because they have more energy now. They can do that. When you get more energy, you move around. Think about little kids that have lots of energy. They move around all the time. So then as the temperature rises, it gets to 100, and then it stays at 100 for a while. And that's when it starts to boil. All that energy in there is going towards making the phase change into a gas now, because that's what's happening when something boils. And you can see there, a lot of scientists use the word water vapor instead of steam. It's kind of debatable. You can think about steam if that's a little easier for you. But also keep in mind that water vapor is actually all around you all the time. It's in the air naturally. It's a big part of our atmosphere. On humid days, it feels humid because there's more water vapor. If you lived in a very dry climate, which we do not, you would not feel quite as much water vapor in the air. And you can see that the particles of the water here in the gas state are much more randomly distributed, and they're trying to show that they're moving around even more. So before we go on to this, I would like for you to answer that question at the bottom about my favorite movie once again. At the end of The Wizard of Oz, the witch says, I'm melting, and she starts to kind of shrink down and sort of fumes a little. Do you think she should have said something else? Is melting an appropriate description of what was happening there? And if you have never seen the movie, or you just want to see it again, pause the video, and there on YouTube, search Wizard of Oz, the witch scene melting, and there's plenty of options that come up, and you can watch again right now, just to see what you think. And then you can answer that question and move on to that diagram that's on the back there. Go ahead. Alright, so on the back you have a diagram that looks like this one here on the screen. And I want you to fill in the ovals with the word ice. So that's a solid. Water, so we're talking about liquid water there. And steam, so we're talking about water in the gaseous form. And I want you to come up with the words that go into the arrows. So here's an example. Ice to water is called melting. The name of the phase change that goes from solid to liquid is called melting. So anytime a specific substance, a physical change only, nothing chemical going on, goes from a solid to a liquid, we say that it's melting. And every substance that's a pure substance has its own specific melting point that happens at a specific temperature, given the normal pressure conditions. Some of these words, there might be more than one possibility. So if you come up with one and somebody you know comes up with something different, don't panic, it's okay. If you need to search the internet, that's fine. If you need to look in your book, that's fine. But please fill in the other arrows, and then when you turn in your worksheet, I expect to see that diagram all done. So that concludes our part for states of matter. So we're going on to some more math. I know you are so excited. I'm excited. See, that's me there dancing around because I love math and I think math is cool. Alright, so there's a nice yummy plate of brownies, or pan of brownies, I should say. And look, I'm going to cut the brownies up, and you can count there, and you see that there are 10 pieces. And if I look at just one of those 10 pieces, that's a fraction. That's called 1/10. That's what a fraction means. That means that you had a whole plate of brownies and that you cut it into 10 pieces, and one of those tenths is that fraction there. So 1/10 is one of the 10 pieces. Now in decimal form, 1/10 is written 0.1. It means the exact same thing. Decimals and fractions, they mean the same thing. They're just written in different ways. What if I cut the brownies up into 100 pieces? And if you don't believe me that there are 100 pieces, you could count them individually. Or you could go through and you could, see, a lot of people, I don't know if everyone uses this trick. I see a lot of people counting things by hand. But if you count how many rows high it is, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, by how many rows across, or columns I should say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something that is 10 by 10, you can just multiply, and 10 by 10 is 100. That means that there are 100 pieces here, and if you don't believe me, you can sit there and count them yourself. So this is 10 little pieces of 100. But notice I kept this area of the brownies the same. It's still that little red shaded corner that was 1/10 before. Now we're just calling it 10 100ths because it is 10 little pieces out of 100. So that's what that fraction means. It means that the whole thing was cut up into 100 pieces, and now we have 10 of them. So 10 hundredths. And the way you write that as a decimal is 0.10, which is equal to 1/10. it was the same thing, because it's still just this little corner of the pan of brownies. So 0.1 is equal to 0.10, is equal to 0.100, is equal to 0.1000. You can keep adding zeros on there forever. It does not change the actual value of the number. As long as you're talking about at the end of the number after a decimal point, those zeros don't change the actual value. I noticed a lot of people having trouble with that in class. It changes the number of significant figures, which I know you love significant figures. You were just waiting for me to mention them. But significant figures have nothing to do with the actual amount. So all of those numbers on the screen right now, they are the same amount, whether we call it 1/10, 10 hundredths, 100 thousandths. That's what this one is, 100 thousandths. And this is 1,010 thousandths. So just because you're putting more zeros there at the end of the decimal does not mean you are changing the value. If you have trouble with that, please come talk to me. I'm very happy to help people after school. But unfortunately, a lot of people just don't ask. So, fractions and decimals are used to show parts of a whole. That is what their purpose is. So, anytime you have 0 point something, that is something that's less than 1. Because 1 is one whole thing. Any decimal, 0 point anything, is less than 1 because it's just a piece of a whole thing. And as long as you have a fraction where the numerator is smaller than the denominator, it's the same way. That's also less than 1. So, quick little review about adding and subtracting fractions, because I know it's been a long time since you've done those. And we just need to get a better understanding about how fractions work, because I've noticed in the past as students get close to having to solve algebraic equations that have fractions in them, they don't know how they work. And they end up writing them the wrong way and getting the wrong answer, so we're just going to do a little review of fractions. I can't add 2/3 to 1/2. It cannot be done the way it is. It's like having to add different things together. Like if I said you have 2 apples and 3 chairs, how many pieces of fruit are there? Chairs are not fruit. You cannot add them together. So if you look here, these are thirds and these are halves. I cannot total that up because they are different things. We have to be able to change them into something that's equivalent to each other. Now both 2/3 and 1/2 can be expressed differently in sixths. 2/3 is the same as 4/6, and 1/2 is 3/6. So see, now that we are comparing the same thing, sixths and sixths, I can add or subtract this. So 4/6 plus 3/6 equals 7/6, which when we simplify or reduce it, whatever your math teacher calls it, it's 1 1/6. If you're not sure how that works, make sure that you ask. Now for multiplying and dividing, I don't have to do that. I don't have to change the denominator. I don't have to worry about them being the same. That's okay. The rule does not apply here. All you do is you multiply the tops and you multiply the bottoms. Numerator times numerator, so 1 times 4 is 4. And then denominator times denominator, so 4 times 3 is 12. And then if you need to simplify that, you should. So 4/12 is the same as 1/3. So that 4 goes into 4 one time, and 4 goes into 12 3 times. Once again, if you have questions about that, make sure that you ask. Now when you're dividing, we can't quite just do the same thing there. We have to flip it over, and that's not the kind of flipping it over I meant. But let's see here. You just flip the second fraction. You come up with its reciprocal, which just means flipping it over. And then you multiply just like you did when you multiplied the other fractions. So I have, 1/6 divided by 2/3 became 1/6 times 3/2. And I just multiplied like I did before, and I get 3/12. Then I simplify that, and I get 1/4. So go ahead and make sure that you pause there and summarize the procedures for both of those things. And then we'll move on to the last part of the video about some basic atomic theory and what the atom's made of. Alright, so in elementary school and middle school, a lot of teachers end up teaching with a model that looks something like this. And it's kind of a no-win situation. The atom does not look like this. It doesn't. We have no evidence that indicates that that's what an atom looks like. The problem is that an atom is so complicated, we can't come up with an accurate drawing or model that's understandable by young children when they're first learning. So this is the best model we can come up with because it's very, very basic. Unfortunately, that leads to misunderstanding later when you get into harder classes. And I know that that's frustrating, but just try to understand that we are expanding your understanding of the atom here. And that while this was okay maybe when you were a young child, you'll find out that this really isn't quite the picture. Here's a diagram that we actually use a little bit more, and you can see this fuzzy area out here. We refer to this as the electron cloud. The thing is that electrons are incredibly unpredictable, and pretty soon you'll learn about a theory that says that you can't actually know where an electron is and how fast it's going at the same time. They're too unpredictable to know both. You can know one, or you can know the other. You can't know both. So we say that there's an electron cloud out here because we know that it's likely that the electrons are in there somewhere. And then the center of the atom, every piece of evidence we currently have indicates that that's the nucleus. It's very densely packed. It's got protons and neutrons in there, and that's what that little arrow is pointing at. That is the nucleus. That's the center. But a lot of this electron cloud is actually empty stuff. There's a pretty good amount of space in there, even though one atom as a whole is actually incredibly tiny. So here we have a rundown of the different parts of the atom and our current understanding of them. So around 1900, we started to notice that the atom was made of smaller parts. Prior to that time, they thought the atom was indivisible, that was the smallest thing that was there, that it didn't get any smaller than that. So there was the electron, and that was discovered by J.J. Thomson in England, and we found that it has a negative charge, and it weighs almost nothing. A lot of physicists, they won't even consider the mass of an electron in calculations because it's so incredibly tiny that it doesn't make a whole lot of difference. They move very quickly, and they're very erratic, and they're more towards the outside of the atom, like in that diagram we just looked at. And then there's the nucleus. That was discovered by a guy named Ernest Rutherford, and he was in New Zealand. He did a very famous experiment with gold foil, and that allowed him to find out that the center of the atom was dense, meaning like closely packed together, kind of like if you took a piece of paper and balled it up really, really tight. That's what the center of the atom is like. That's the nucleus. And then he found out that it was positively charged. Rutherford continued to do some more experimentation from there, and he found out that there was the proton, and that was one of the things that was inside the nucleus. For a while, they thought that was the only thing in the nucleus, because it was positively charged and, comparatively speaking, had a relatively heavy mass. Now, protons themselves, they're not heavy, of course. They're incredibly small, incredibly light, but compared to the electron, are pretty heavy. Over time, they realized that the proton was not enough to account for the mass of the nucleus, so there must be something else there. So they named it the neutron, and that was discovered by Rutherford and another scientist that was working also called James Chadwick. And they concluded that they couldn't have had any charge, though, because we've already accounted for the positively charged part of the nucleus. So they thought that its only function of the neutron was to make the nucleus heavier. So its main thing is that it accounts for a lot of the mass that's in an atom. And the number of neutrons can actually vary. For example, carbon, it can have 6 neutrons. It can have 7 sometimes. Those are called different isotopes of certain elements. And we've been talking about that a little bit in class and doing some activities about it. And it confuses a lot of people because they think, well, if it has 7 neutrons, how is it still carbon? And it's okay. And I understand that it's confusing. It's only the protons that control what the actual element is. The neutrons can vary a little bit. And it's possible that there's some isotopes even that are so rare that we might not have any evidence of them. And maybe we'll go on to be a chemist and discover some new isotopes. So you can see here you have this diagram. We've been working with this some in class. So this over here will always be the chemical symbol, which you've been working on memorizing for a little while now. And then over here to the left, a lot of times you'll see two numbers, and it looks like it's a fraction, but that is not a fraction. It's not the type of fraction that we saw earlier in this video. It's just two numbers written over there to the left, one on the top and one on the bottom. And the top one is always the mass number. That's going to be the bigger of the two. If you ever look at this and you see a smaller number on the top, there's a chance that there's some kind of mistake. On the bottom, that's the atomic number. That's the number of protons. That's the number of the element on the table. So it goes from 1 to 118, depending on which periodic table you're looking at. The one on the wall in our classroom at school, it only goes from 1 to 112 because it's a little bit older. So those numbers that go in order, starting at number 1, that's the atomic number. And that's the number of protons. So if you would go ahead and make sure that you fill the rest of this in. And thank you for watching. And don't forget to turn in your worksheet on the due date. And I'll see you later. Bye.